All right, now that we've discussed kind of how to write parametric equations, we're going to talk over parametric equations of a very special type of function, and that's going to be parametric equations for lines. And parametric equations for lines are going to be defined in terms of two different things. Just like you're used to being able to write lines as y equals mx plus b in terms of slope and intercept, we're going to write parametric equations for lines in terms of points and vectors. So a line through the point x0, y0, z0, and in the direction A, B, C. And using those two different types of notation, that could also be AI hat plus BJ hat plus CK hat. Has the following equations. We can write it in parametric form as x minus x0 is equal to AT, y minus y0 is equal to BT, and z minus z0 is equal to CT. For any values t that we might plug in, because lines kind of go on forever. Or we can solve these equations real quick. And let me actually write that down. So if I just solve these for x, y, and z, the actual coordinates, that gives me x is equal to AT plus x0, y is equal to BT plus y0, and z is equal to CT plus z0. Those are, again, my x, y, z coordinates at a single point along the line, could be calculated according to those formulas, same way we did with x and y before. And so I can also, actually I'll do it on its own line. That's our parametric form. Or it can be written as the vector that just has those three components. So r would be equal to AT plus x0 I hat plus BT plus y0 j hat plus CT plus z0 k hat. And you could write that in those three components in angle bracket form, but we'll just kind of use those interchangeably whenever we feel like it in this class. And the reason I'm giving you this vector form right here is because we'll be working a lot more with vector forms. They'll come back for us in section 10.2, I think, and your web work is going to take some answers in this form. So the line can be specified either as three separate equations or kind of packed into one vector that represents that we would plot these three components separately in the x, y, z coordinates for any t value that we choose. And so let's go ahead and just see how this equation works. So a line through the point, let's see, 3, 1, 4, in direction -1, 1, -2, is going to be given by, here, what we'll do is we'll write the formulas right here. And that's our x0, that's our a. The thing attached to time comes from where we're going, in what direction. The thing next to x is just the point we reference ourselves from. So we're going to have x minus 3, that's our x0, is equal to -1 times t. And then y minus 1, just reading it from right here, is equal to t times 1, that 1 coming from right there. And then z minus 4 is equal to minus 2 times t. Or if we wanted to use that vector form, we could say it's along this vector r, where our x-coordinate is given by 3 minus t, our y-coordinate is given by 1 plus t, and our z-coordinate is given by 4 minus 2t. That was just some real quick algebra right there where I solved for x, y, and z in each component of that vector. And I went through that quickly just because I want to be able to get to lots of examples in the time we have. So if you need to pause and kind of like check that all works, go ahead and do that. But the thing I just wanted to show you here is how the equation works. And in general, to write the equation of a line, we just pick a point, find the direction, then plug both into the formula. The only thing is that this step in the middle, finding the direction, might take a little while. Depending on the information given to you, there might be a couple extra calculations to figure out what that direction is supposed to be.